let's just get to it. This is chapter 21 from OpenStack Physics. It's about circuits. I want to start off, and I'm doing a chapter summary. I want to start off with the most important ideas from chapter 20. And if you watch my chapter 20 summary, some of the things I'm going to cover today, I covered then because I was just thinking ahead and I wasn't following along. But that's fine. You can double cover. Okay, so number one thing in chapter 20, this is chapter 20. Let's put chapter 20. I have this. This is the definition of electric current. This says that electric current is the motion of charges. So if you have some charge delta Q moving through something in a time delta T, that's the current. Charge in coulombs, time in seconds, coulomb per second is an amp. Okay, now we have another definition for current, NEAVD. That's right, I always get that one messed up. It is, what is Q? This is another way to describe the current, where N is the number of charge carriers per cubic meter. Q is the charge of those charge carriers. A is the cross-sectional area of the wire. And then VD is the drift velocity. Now, the book doesn't tell you this, but I will tell you this. The drift velocity depends on the electric field inside of there. So remember when we talk about metals in electrostatic equilibrium, the electric field is zero inside. Otherwise, the charge would move around. But if you're able to create a constant electric field inside of there, you can get the charges to move. This is what we call the electron mobility. And the most important thing there is that it helps us make a connection between electric field, change in electric potential, and electric current. And the book doesn't really go into that, but I want to point it out for myself. And I may give you a demonstration of that later, but I'm not sure. I have a lot of other things to do too. So, okay. That's the definition of current. The other huge thing was this. I'm going to write it the way they normally write it. V is IR. This says that if you have some wire and there's a current flowing through it, I, then the change in potential, delta V, which is called V, we call it V because we're dumb. It's really a change in potential from one side to the other, depends on properties of that material, which we call resistance. And we would normally write that as a resistor. So the voltage drop across a resistor depends on the current. V equals IR. That's what you get. Now, if I have a wire like that, I can write its resistance as R equals rho L over A. So this rho is the resistivity. This says that that's a property of the material. These are properties of the dimensions of the wire. A longer wire has a more resistance. A thicker wire has less resistance. And then finally, there's one other thing in that chapter, power equals IV. So if I have current flowing through something with a change in potential, that's going to consume power in watts. So if that's current in amps, the potential in volts, amps times volts gives me units of watts. And it kind of is a big deal. It's useful for a lot of things too. Because I like to focus on energy and power. Remember, power is the rate of change of energy, not electric field. Okay, now we can erase the zero and go to chapter 21. There was other stuff in there. There was stuff about AC circuits, but I'm just keeping to the bare basics. Okay, number one is to look at resistors in series. So if I have a resistor and then another resistor, we'll call this R1 and we'll call this R2. These would be in series. So we define two elements as being in series if they have the same current I going through them. So if there's a current I going through this resistor, it has to be the same current going through R2. There's no other way, right? So then that is how we define objects, elements in series. They could be resistors, they could be something else. But those are resistors in series. Now, let's suppose that I have three. I'm going to do three resistors in series. They all have the same current flowing through them. So what if I wanted to measure the potential difference across the whole thing? Using Ohm's law, V equals IR in general, I can say the voltage across the whole series is going to be this voltage plus that voltage plus that voltage. So I'm going to say V equals V1 plus V2 plus V3. But what's the voltage across this? Well, it's I times R1 plus I times R2 plus I times R3. And since they all have the same current, I can factor out the current. R1 plus R2 plus R3. So suppose I take those same three resistors and replace it with just one, R equivalent. Or the book calls it RS for R series. And I want to have the same current going through that, then I can say the voltage across that resistor, I times R series is going to be I times R1 plus R2 plus R3. So R series is equal to the sum of the individual resistors. It's just a consequence of being in series. That has to be true. And you can have 3 resistors, you could have 4 resistors, you could have 10 resistors. It doesn't matter. If they're in series, you can just take their values and add them together and replace that with just one equivalent resistance. Now, there is, I want to say, something also very useful about resistors in series. And it's not in the book, really, but it is. And it's called a voltage divider. So let's say that I have these points, and this is R1 and R2, and there's a current flowing through there, I. If I measure the voltage across this whole thing, let's just call that V. But then I could also measure the voltage across this, and we'll call that V1. I can measure the voltage across this, let's call that V2. So V is going to be equal to, well, let's just say V1. V1 is equal to I times R1. V2 is equal to I times R2. So, but the ratio of voltages in terms of this, because I know that V, the total V, is I times R1 plus R2 because those are in series. So let's solve this for I. I get I is V over R1 plus R2. And if I put that in right here, I get V1 is V R1 over R1 plus R2. And that looks dumb, but it is a voltage divider, right? So imagine that R1 is 10 ohms and R2 is 10 ohms. Well, then I put 10 divided by 10 plus 10, so 10 over 20 is half. I get half the voltage drop across that and half across that. What if I change this to 40? Now I have 10 here, 40 there, so it's going to be 10 over 50, so it's going to be 0.2. So I can change how much voltage I have across each resistor, and I can get the voltage drop that I want using these two resistors in series. That's why it's called a voltage divider, not in the book. Okay, now let's jump to resistors in parallel. Reminder, this is a chapter summary. This is not the chapter. I'm going to start off with 3. R1, R2, R3. So we define objects in parallel. Is it 2 L's? Is it parallel? Is that right? I don't know. You kind of can't spell things when you're at the board. They are in parallel if they have the same change in potential. So if I measure the change in potential of this, since there's nothing in between these two, then the change in potential across that and that have to be the same and that have to be the same. So they all have the same change in potential. Now, another thing that we know, and we'll look at this later, if I have a current coming in, I, then that current's going to split into 3 different pieces, right? So all the current can't go through all the branches. So let's call this I1, I2, I3, and we know that I has to be equal to I1 plus I2 plus I3 because charge is conserved. So what about the voltage across R1? Well, I know V1 is I1 times R1. V2 is I2 R2. V3 is I3 R3. That's a 2. But all these are the same voltages because they're in parallel. So let's solve this for I1, I2, and I3. I get I1 is equal to V over R1. I2 is equal to V over R2. I3 is equal to V over R3. So if I put those in this equation, I get I equals I1, which is V over R1, plus V over R2, plus V over R3. Now suppose I replace this with one equivalent resistor, RS, that has the same voltage drop across it and the same total current going through it. Then I could say the current for this is just going to be V over R parallel. I'm sorry. That's how they do it, parallel. And that's going to be equal to V 1 over R1 plus 1 over R2 plus 1 over R3. Notice I factored out the V. Now the V's cancel and I get the following relationship for resistors in parallel. 1 over R parallel is 1 over R1 plus 1 over R2 plus 1 over R3, and so forth. And again, you can have as many resistors in parallel as you want. You just take the fractional resistances and add them up, and it's equal to 1 over the resistance. Now be very careful, okay? Don't take fraction, 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 and that's the resistance. That's not the true. You got to add these all up and then take the inverse. And I do want to show in one particular case, there is a current divider, same idea. The ratio of currents going through each one depends on the resistances, but I want to show you something else. Suppose I just have two resistors. In parallel, R1 and R2. Then 1 over R parallel is 1 over R1 plus 1 over R2. I can get a common denominator, and that would be R1 plus R2 over R1 R2, right? Because I'm going to multiply this by R2 over R2, multiply this by R1 over R1, common denominator of R1 plus R2, and then I add this. I can now combine the tops. So this says R parallel is R1 R2 over R1 plus R2. That only works for two resistors in parallel, okay? But you'll notice that since I'm multiplying these and dividing by the sum of those, the equivalent resistance has to be less than each individual resistor, right? Okay, so let's say I put, they're all the same. I get R squared divided by 2R, so I get 1/2 R. So it's going to be a reduced resistance when you put things in parallel. You can think of that as putting two resistors next to each other, and you're increasing the surface, the cross-sectional area, which in our previous chapter says the resistance would also decrease. Okay, moving right along. I wrote down some notes so I wouldn't forget what was in there. Batteries and EMF. So a battery, we can think of a battery as, I like to think of a battery as a capacitor. It's not a capacitor. Okay, this is just a model. Suppose I have negative charge on my capacitor right here and positive charges over there. Well, this is going to create, if I connect this to a resistor, which we will do later, this is going to mean the negative charges over here are going to move this way. So I'm going to have a current going this way, and we're going to get a current running through this. But that current means that this charge is going to decrease, and so it won't last forever, and we will look at that. What a battery does is it essentially takes a little conveyor belt inside of here, not actually, and this will move, let's say we have negative charges, this is going to move negative charges from the positive side to the negative side. So it's going to maintain a charge difference. So that means that you can still have a current flowing because of that conveyor belt in the middle. Let me get a battery. This is a D-cell battery. It does not have a conveyor belt in there, but what it does have is a chemical. And that chemical is a chemical process that moves charges from one side to the other. And because of that, we call this battery an electromotive force. And it has units of volts. It's not a force. It's an older term, but we see it all the time. EMF is the voltage across the battery. It's the driving force that moves charges from one plate to the other. It's almost always a chemical process, but not always. But I think almost always. Okay. So this is a 1.5 volt D-cell battery. Now, let's address the next question. Very important. If I have a D-cell battery, 1.5 volts, and then I take 8 of those, and I put them in series. So it'd be like this. Eight of them. I'm not going to draw them all. In series, it'd be 1.5, 1.5, 1.5, 1.5. So the voltage of this whole thing would be 12 volts. Right? Now, can I take those 8 D-cell batteries, 12 volts, and replace my car battery? My car battery is also 12 volts. Could I replace these 8 D-cell batteries with my car battery and start my car? And the answer is, well, you know the answer. Hopefully you know the answer is no. You cannot do that. Even though they have the same voltage, those are different things. It turns out that your car battery, when you start that starter motor, you're going to get 50 to 100 to 200 amps, depending on the kind of car that you have. That's a lot of current. You're not going to get 50 amps out of a D-cell battery. Why? But why? Well, we can model an actual battery with the following. So here's my battery. There's my D-cell battery. So inside we have terminals. I'll put this as its terminal. Let's see, that's the positive side. So that's my positive terminal of the battery, and that's my negative. But there's also what we call an internal resistance. I'll call it Ri. The book uses this lowercase r. So this is EMF, and that's Ri. So we can model this actual battery as having a little resistor inside of there. Say that this is a 1.5 volt battery, and I connect this to a 10 ohm resistor. And you may say, well, hey, 10 ohm resistor, I would get V equals I R. So I would be V over R, 1.5 over 10, 0.15 amps. But that doesn't happen because of this internal resistance. So let's say this has an internal resistance of 10 ohms. Then if I do my situation here, if I look at the current going through my battery, my effective battery terminal is going to drop because I have a 1.5 volt battery, and then I have minus I times R. So if I have a current coming out of there, this is going to be a voltage drop because of that internal resistance. And that means that I can't get an infinite amount of current out of this because of that internal resistance. So if you take this and hook it up to your car, and you try to start the car with 8 of them, then the voltage on this is going to drop because of that internal resistance. And it's a way to model a battery. Okay. Now, this also comes over. You could start a car with car batteries, but you have to do this. I have to put the batteries in parallel and in series, because as I put these in parallel, and they all can have a certain amount of current that can come out of them, but I can add all those currents up. So it is possible to start your car with D-cell batteries, but because of internal resistance, it's impossible. I'll do some internal resistance problems because it's fun. Okay. really, two main things left. This is not super important, but I'm going to show it to you anyway. Imagine that I have this. I'm going to just draw a diagram. Battery, resistor, 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 resistor. So you'll see things like this, a circuit with multiple branches, and there's two ways to deal with this. One way, if I only have one battery, I can actually reduce this to the following. I can reduce this into a simple circuit with just one equivalent resistance. Now, to do that, I have to go look at this and say, okay, I need to find resistors that are either in series or parallel. So like right here, these are not in parallel, and they're not in series. They're not in series because they don't have the same current through them. These are not in series because there's not the same current. These are in parallel. So I actually could use my equivalent resistance and replace those resistors with one equivalent resistance. And then once I do that, now these are in series. So I could replace these with one equivalent resistors. Now these are in parallel. I could replace those with one equivalent resistance. Now those are in series, so I can replace that with equivalent resistance. And that's one way to solve a problem. I wouldn't recommend it, but it is a way to solve a problem. Now, there's another way to solve a problem that's more generic because it allows you to have batteries in there too. So let's write a circuit. I'm making up something here. That's good enough. I couldn't do these as being in parallel because there's a battery right there. They don't have the same voltage across them. And then nothing's in series. I can't reduce that. So instead, we're going to use two rules. These are what's called Kirchhoff's loop rules. So Kirchhoff's rules. So the first one says that if I have a junction and current coming in, I'll call that I in, and this would be I1, I2, I3. Since charge is conserved, the current coming in has to be the current coming out. We can write this as I in equals I out. And I'll set that up in this diagram right here. So we'll call this EMF1, EMF2, R1, R2, R3. So that's my first rule. The current coming into a junction is equal to the current out. The next thing is that remember that potentials are a conservative thing. It doesn't matter about what path you take. And if it doesn't matter what path you take, a complete loop has to have a zero potential. So if I add up the potentials around any loop, delta V around any loop, it would have to be zero. And these two rules can allow me to create some equations for which I can solve this problem. So let's label our currents here. Let's call that I1. I'm going to call this I2. I'm picking a direction, even though I don't know for sure what it is. And I want to find these three currents, I1, I2, and I3. Let's write down the junction rule. So here I have a junction, and I have I1 coming in, and then I have I2 and I3 leaving, so those have to add up to I1. So that's my junction rule. Now that has three variables in it. So I have three variables. I can't solve that, right? I need to know two of the variables, and I can solve for the third. But in order to solve three variables, I need three equations. I can get two more equations from the loop rule. And in this circuit, there's actually three loops. I could do this loop, I could do this loop, or I could do this loop right here. Okay, so you only need two of those loops. I'm going to write down this loop. I'm going to show you how to do it. We're going to start here, and we're going to go around the loop and add up the voltages. And if I go in the direction of the current, the voltage across the resistor is negative. If I go across a battery, I can just look at the positive and the negative side. So here, I'm going to go across the battery, and I'm going to get a positive voltage drop. So I get E1. Now I'm going in the direction of the current. I get minus I1 R1. and then I'm going to go in the direction of this current. I get minus I2 R2, and then I get back over here, so I'm at 0. And so that's one loop. Okay, I have two more variables in there. So now I have two equations, three unknowns, still don't have it. Now let's do this entire loop, the big one. It doesn't matter which ones you pick. Let's go across, starting from here. I get plus E1 minus I1 R1. Now over here, I'm going from the positive side of the battery to the negative, so I get a minus E2. And now I'm going in the same direction as current I3, so I get minus I3 R3. Now I'll come down here and I'm all the way back and I get to 0. Now I have three equations, three unknowns, and I can solve it just with basic algebra principles. And I'm not going to do that. We'll do that as an example in another video. Now you may say, why don't you use two junctions? Well, if I use this junction down here, I'd have the current coming in is I2 plus I3, and that would be the current coming out I1. That's the same equation. The same thing's true. If you try to choose three loops, you're going to get redundant equations. You have to use at least one junction rule in order to get the whole thing to work out. But those are Kirchhoff's loop rules, junction, loop rule. There's a here about the Wheatstone Bridge, which is really cool, but I'm running, this is going a little bit longer than I wanted to, so I'm going to skip that for now. Let's talk about the last thing, and that's an RC circuit, because it's really cool. We talked about it briefly, and I'm going to show you how to model this with Python, but you can't really model it in this class. You can't determine exactly what happens. So imagine that I'm going to start with a simpler case. Imagine that I have a capacitor, and it's charged, it has a charge Q on there. And then I connect that to a resistor, R. When that happens, there's a potential difference across the capacitor. Q, V is Q over C. V capacitor. So let's apply the loop rule. So the loop rule says that if I go across this loop, I should get 0. Well, there's going to have to be a current I, because as I go across here, I have Q over C, and then I have minus IR, and that's equal to 0. Right? If I go all around the loop, minus IR is a voltage drop across that. Now, this is actually a very difficult problem, because we have a current, but that current comes from this charge. So when the current is flowing, that's going to reduce the charge on here. Remember that I is dq dt, delta q delta t. So this is a very difficult equation to solve, but as you realize that if I have a current, I'm going to decrease this voltage, which decreases that current. So it's a loop problem. You can solve it with differential equations. You can solve it with Python. I'll show you how to do that. But in general, if I start off with initial voltage of V0, then the voltage across that as a function of time would be V0 times E to the negative T over RC. So R is the value of the resistance, C is the value of the capacitance, and this is the natural number T. I mean E, the natural number E. So this says that if I plotted voltage as a function of time, it would do that. It would decay. V as a function of time. Now, what if I have a battery in there too, and the capacitor is not charged? So that would be like this. I'm not going to solve this problem, I'm just going to tell it to you. So if I have a battery, a capacitor, and a resistor, well now in this case, the loop rule says that initially I'm going to have some current I, and there's going to be no charge in the capacitor, so there's no voltage drop, but I will have a voltage drop across this. And if you want to find the voltage as a function of time, it looks like this. Voltage is going to be EMF, the battery EMF, times 1 minus e to the negative t over RC. And so this would look like this. It would charge up until it reaches, this is the voltage across the capacitor, until it reaches some constant amount. And the important thing here is to realize that that capacitor, if it's uncharged, it's going to initially act like it's not even there. There's no voltage, there's no charge, there's no voltage drop across it. It's not even there. Over time, charge builds up, and as charge builds up, the voltage across this is equal to the voltage across that. So the loop rule says that there's no current. Okay, so this is going to be a decrease in current, an increase in voltage across the capacitor. Sorry. So that's that. And again, you can't derive that equation without using some differential equations. I can show you how it works in Python, but we'll do that later. Okay, let's do a quick chapter summary. So what are the most important equations in here? First we have this. The resistance, equivalent resistance in series is the sum of the resistors. The equivalent resistance in parallel is 1 over the resistance is 1 over R1, 1 over R2, plus 1 over R3. Okay. The voltage across a battery is EMF minus I times R internals. That's for real batteries. Then we have the loop rule. Delta V loop is 0. And the junction rule, I in is I out. Finally, we have this V equals EMF 1 minus e to the negative t over RC, or V as a function of time is V0 e to the negative t over RC. So that's charging capacitors, and that's discharging capacitors. And that's that. I'm waiting for my thumbs up for my video. There we go. Okay, great. So read the chapter. There's a lot of stuff in there about like Wheatstone bridges, applications, how to measure things with voltmeters. It's important stuff, but I'm focusing on the most important fundamental things. We'll do voltmeters and things like that in lab. Okay, hope that helps.